Iriux Almodovar. Next presentation. It's entitled Towards the Development of Sustainability Chemistry Teaching Laboratories, an approach from green chemistry principles and life cycle analysis. A brief story of Professor Almodovar. She obtained her bachelor degrees in chemistry in Universidad de La Habana in Cuba. She was honored with a DAAD scholarship to pursue her PhD in chemistry at the University of Chile. Then she was awarded with a postdoctoral grant at Professor Bruce Castle's group at the University of Chile. And then she got a position here in Universidad de Santiago de Chile, where she has been a professor of organic chemistry and at the Faculty of Chemistry and Biology for more than 10 years. Her fields of research are organic chemistry and physical organic chemistry. Driven by her interest in organic chemistry, she has developed courses by its instruction. She is actively engaged in a sustainability project for the faculty aimed at evaluating the environmental impact and ensuring adherence to the 12 principles of green chemistry in teaching laboratories. Through these efforts, she aims to advance sustainable chemical processes and educate future generations in this perspective. Professor Almodovar, please welcome to the stage.
Thank you very much for being here today. Sometimes I have to read because I forgot the English. This is the work I was developed with some colleagues from University, from Faculty of Engineering. The teamwork is comprised by Andrea Espinosa and Lorena Espinosa from the Faculty of Engineering and myself, Iriux from the Faculty of Chemistry and Biology. As you know, University of Santiago de Chile is one of the oldest universities in Chile and the most prestigious university in Chile too, hosting more than 25,000 students. Universities play a key role in building sustainable societies by shaping socially responsible individuals. In this sense, several Chilean universities, including University of Santiago de Chile, have committed to promote sustainability through the Sustainable Campus Network by signing the second introduction agreement in sustainable higher education. Each institution is expected to explore alternatives to minimize the environmental impact of their work. Yes? Within the university academics activity, they are engaged in laboratory practices, most of them in Faculty of Chemistry and Biology. These spaces consume more energy and water than offices and produce tons of plastic waste each year. It is worth mentioning that these laboratory practices are done by many students, not only of our faculty, but also of the faculty in the university. So this impact is multiplying by each students that use laboratories. In this presentation, we will show the results from an initiative that we will carry out with people from the Faculty of Engineering, we evaluate the environmental impact of organic laboratory, organic teaching laboratories, by evaluating compliance with the 12 principles of green chemistry and conducted a life cycle assessment. These approaches are different but complementary. What we do in this case is we work in parallel at the Faculty of Chemistry and Biology. A group of students have analyzed an organic chemistry teaching laboratories, one of them, and at the same time in the Faculty of Engineering, the students carry out the life cycle assessment to the same laboratory. This is it's very important that students with different backgrounds work collaboratively, because they can make better comparisons and they can learn from each other and obtain better results. Well, green chemistry, the definition of green chemistry is invention, design, and application of products and processes to reduce or eliminate the use or generation of toxic compounds. The aims of green chemistry is to reduce risk to human health and environment, and try to avoid to be in contact with hazardous compounds. These are the 12 principles of green chemistry that guide us in this sense. I like to say that these are the 12 principles that John Warner was talking about, that we have to apply when we work at the lab, trying to change the things we are doing okay, in the lab. The benefits of applying green chemistry are well known, since with the application of the 12 principles of green chemistry, we can get improved resource use, increased energy efficiency, and reduce human and environmental hazards. I also have to say that applying the 12 principles of green chemistry is a more ethical way to make chemistry, because safety is a priority in green chemistry. There are too many approaches to quantifying the compliance with 12 principles of green chemistry, but we decided to use dosing tool to make the evaluation, because dosing tool is quantitative evaluator designed for industry first, but we can use it as academics for teaching and also for research. I decided to use dosing because, well, it's free. It's free, and it's easy for students to use it. And the thing I like the most is that when we use dosing, we students have to analyze in deep the safety data sheets of the compounds. Yeah, and normally in the labs we never analyze the safety data sheets, and we don't know if you are working with hazardous compounds, how hazardous it is. Sometimes, or most of the time, we don't use it. And when you are applying dosing tool, you have to study deeply this resource. The reactions we selected was elimination reaction. There is students from the faculty know these reactions. These are the reactions that we use the most in the laboratory. All the careers use or apply these laboratories. Yeah? Elimination reaction and nucleophilic substitution reaction. This is a brief description of the reaction, of elimination reaction. We have to use drops of orthophosphoric acid. We use cyclohexanol, and we obtain by heating cyclohexane. We have to perform a fractional distillation to get the product. This is an excerpt of the safety data sheet of the cyclohexanol. Here we can see all the toxicity or the aspect about the hazard of the compounds. This is what students have to read to fill the dosage tube. These are the results we obtain for elimination reaction. When we use dosing, the results have been used for comparing with another process, another similar process. In this case, we haven't done that, but I think that information is important to that. So we have the principles of more concern are related to reduced human and environmental hazards. So if we propose another reaction, similar reaction, we have to try to improve the principles related to these conditions. This is the other reaction, the substitution reaction. They will use terbutyl alcohol, an excess of hydrochloric acid, and an auxiliary calcium chloride. We have to neutralize it, passive neutralization, and fractional distillation. In this case, using excess of one of the reactant and using auxiliary cause that we produce more wastes. This is the results from the dosing tool. So in this case, the principles of more concern are related to improved resource use, because some of the resources are wasted at the end of the reaction. The next steps, once the students calculate the 12 principles of green chemistry, they have to search or create new experiments of the same time of reaction, calculate again the compliance with the 12 principles of green chemistry, and select the green one and implement it in the laboratory. The life cycle assessment is a modeling approach to evaluate a process or product, the whole life cycle of the process or product. With the results, we can, for example, compare different process, the impact of different process, and to identify the origin of the impact. The program we used to make the evaluation was CIMAPRO, and the database is EcoInvent. The impact assessment method was received 2016 midpoint and received endpoint. The aim was to gather information on laboratory practices and identify the hotspots in environmental impact generation, so we can fix it. The system boundary we used was cradle to gate. That's it. This is the diagram of the process made by engineers. And the considerations we take into account was the fractional unit was 1 kilogram. The treatment of the waste was not considered because it's in charge of an external company. We have no data. The discarded chemicals were considered emissions to soil. The impact into the infrastructure was not considered because it's extensive use in time. And gas emissions, we are not included because we have not the equipment necessary for measurements. Is the same consideration for the two reactions? And the results we can see here, these are the impacts in different aspects. The phase of the process that most impact is distillation, and electricity consumption in both cases represents an average of approximately 88% of all impact categories, all of the impacts in all categories, excuse me. And in the dehydration of cyclohexanol, the preparation path is the most impact in the process. This is the receipt endpoint that shows the impacts into human health and impacts to the ecosystem. In blue, we have the substitution reaction, and as we saw in the calculation of dosing tool, the substitution reaction was has the most relevant impact into human health and the ecosystem. The final remarks I'm going to read because I want to say all the things. I don't want to forget nothing, so let me read because I put so much emotion in this in this part. So this work constitutes the preliminary phase of a significant endeavor to progress towards sustainable education in chemistry. We aspire to instigate changes not only within the laboratory setting, but more crucially in the mindset of students and the entire university community. During the development of this work, we identify key aspects for consideration in future applications of these methodologies, such as standardizing the functional unit in both approaches and acquire a specific chemical compounds database. We aspire to disseminate these results to the community and extend our efforts to the rest of the laboratory's practices within the Faculty of Chemistry and Biology, aiming to reduce the environmental impact of chemistry education at our university. Thank you very much.
Thank you, Professor Almodovar. Questions or comments from the audience?
I have two questions, sorry. First of all, in which year are these courses being taught that you show the reactions? In which year of the organic chemistry?
In the faculty, it's in the second year. Yes.
And my other question is, how do these students and the people who are using those, they find about the process? Like, do they think how they enjoy it?
They enjoy it at the end with the result. But I think the problem with dosing is sometimes it's not so clear what you have to put in the, to fill some aspects. For example, which temperature I have to put here if I use some different temperatures in different stages. Sometimes there are products that have no safety data sheets because are created here in the faculty, for example. That is one of the biggest problems. We have many doubts when we are filling those into. But at the end, I think it's very useful for students because they realize the problems of the practice, and they can propose some changes. And it's a nice conversation with the students, and they feel responsible to change that. That's it. Thank you.
Hola, muchas gracias por tu presentación. Me queda una duda en una diapositiva que mostraste, que dijiste que el proceso de destilación era el que más consumía.
En ese caso, sí.
Ahí, claro. Que la destilación era el proceso que más gastaba o más...
No, que más impacto produce.
Que más impacto,
sí.
Claro, a nivel de electricidad principalmente.
Ajá.
Entonces me preguntaba a partir de eso, ¿qué acciones se pueden tomar considerando esos resultados? Como que el proceso de destilación es el que más impacto tiene, entonces, ¿qué acciones se pueden tomar a partir de eso?
En este caso, particularmente, podríamos cambiar el laboratorio, buscar otro laboratorio de eliminación donde no sea necesario hacer la destilación para purificar. La destilación impacta más por el consumo energético, más que todo.
¿Pero sería reducir el tiempo de destilación o cambiar la destilación?
No, cambiar el laboratorio, cambiar el práctico, buscar otra eliminación. Si lo que queremos enseñar es eliminación, nosotros podemos buscar otras reacciones de eliminación que no impliquen hacer la destilación. Exacto. Sí. No es muy fácil hacerlo, por eso no lo hemos hecho todavía, pero esto es.
Muchas gracias.
More questions? No?